take a look at this section. Tests for independence, and we're taking a look at two different categories of homogeneous or not. Homogeneous means similar, if you haven't seen that word before. Similar, connected in some way. Okay, contingency table is a two-way table, relates two categories of data. Row variable, each row in a table describes a specific topic. The title of the topics is a row variable. Column variable, each column in a table describes a specific topic. The title of the topic is the column variable. And then a cell, each box inside a table is called a cell. Now here's an example. We're taking a look at hair color and compared to education. Educations are a column variable, and hair color is our row variable. Their high school graduates with red hair would be the cell in the first row, first column. So here we're testing, see whether there's any kind of connection between education and hair color. Now Simpson's paradox says, that describes a situation in which an association between two variables inverts or goes away when a third variable is introduced to the analysis. For example, over here, you might be looking at that and say, well, looks like if you got red hair, then you got this percentage that goes on to college, this percentage that goes on to graduate school. But if you got brunette hair, then you got this percentage. We do 42 over our total. That goes to college, and this percent goes on to graduate school. But maybe there's a third variable that we're not taking a look at. And so that these really, even though they appear to have some kind of connection between them, there's a third one that actually explains what's happening. Here's an example: sex bias in graduate admissions at University of California. And I see men, we got 1,191 accepted. Not accepted is 1,399 for a total of 2,590. Women, 557 were accepted, and 1,278 were not accepted. You can see that there's some real discrepancy here. So it appears like they have some bias against women in terms of the graduate admissions. And there was a lawsuit brought based upon these numbers you see right here. But if we take a look at the programs of study, here we take a look at the relative frequency, and the light blue is men, the light green is women. This is the amount admitted. You see the women are greater in A, greater in B, pretty much the same in C, pretty much the same in D, pretty much the same in E, a little bit more in F, but not pretty much the same. So it appears when you look at it by programs of study that there is no discrimination. So how in the world could this happen? Well, realize that percentages are misleading. This might say 80%, but what is your in? How many are we talking about? If it's 80% of four people, then the numbers really are misleading when you look at the percentages. And this sums it up best. This is according to Sullivan. The initial analysis did not account for the lurking variable program of study. There were many more male applicants in programs A and B than female applicants, and these two programs happen to have higher acceptance rates. The higher acceptance rates in these programs led to a false conclusion that the University of California, Berkeley was biased against gender in its admissions. So when we looked at it with this new category, the program of study, again, the idea here, if there was 4 women applying in this area and 80% of them got accepted, well, maybe that's 3. Over here, though, if we have 5,000 men that applied, but only 60% of them got admitted, then that's a lot more in-wise. I don't know what that would be, but so when you look at the grand total, it skews it. Now, we got test of independence. These tests determine if one variable is dependent upon another variable. Example out of the book is the variable number of hours studying dependent upon another variable major. Now here's our classical approach. Now here we're doing tests of independence, and we got our classical approach, which is kind of time consuming, and then we got our p-value approach we use T84 plus on, and it'll simplify it quite a bit. Let me come down here and write this problem down. Okay, so we got test the claim, and alpha is 5%. I'll come back to the H0 and H1. Okay, so alpha is 5%. And we got red, green, blue. So we're looking at favorite color versus number of children that they had. And seeing if they're independent, dependent, so forth. Now I'll use independent and dependent, but we'll see that it's worded slightly different. So more than 5. Okay, we've got 20, 10, 5. 3, 2, 1. 0. 30, 45, 51. 23. 12, 2 and 7. 8, 12, 3. 4, 5, 7. And 2. Okay, and you want to test a claim about independence. Okay, well, let's go back up to our classical approach. Now, when I said that we'll come back to the H0 and H1, it says that H0 states that the row and column variables are independent. So we're saying that the color, your favorite color, and number of children, number of kids, are, and again, H0 are always independent. The H1 is the favorite color and number of kids are, and I'll say dependent, but that's a pretty strong word. There actually says they are not independent. It goes back to how we did our claims before. Remember, reject versus and reject and accept versus reject and do not reject. To say they're dependent is pretty strong, saying that these are dependent upon each other, because there may be other factors we're not taking into account, like that example I gave earlier about the bias in graduate admissions. Instead, we say that the previous or the favorite color and number of kids are not independent. We're not necessarily saying they're dependent, we're just saying they're not independent. That there appears to be some kind of connection between them. I'm going to go with the independent and dependent. I just think students click better when I use those as opposites of each other. Okay. Compute the row and column totals. So, let's see. 20 plus 30 is 50, plus 8 is 58. 10 plus 45 is 55, 65, 67. 5 plus 51 is 56, 59. 3 plus 23 is 26, plus 4 is 30. 2 plus 12 is 14, plus 5 is 19. 1, 2, 7, that's 10. And 9, I guess. Then if I add over here, 20 plus 10 is 30, 35, 38, 40, 41. Let's see, 75, 70. Okay, 30 plus 45 plus 51 plus 23 plus 12 plus 9, 170. let's see, 23, 27, 27, 32, 39, 41. 9, 14, 18, 21, 23, 33, 41. Okay. Now add these together. This is our grand total here. That's 2, 8, 15, 252. Let's see if this adds up the same way this way. 58 plus 67 plus 59 plus 49 plus 19. 252. Okay, that looks good. So we got our row and column totals. Now also got our grand total because I know I'll need it here. Now this says compute the expected frequencies, E. And even if, I made these numbers up, so even if the E is not at least 5, we'll go with it, just because I want to show the technique. So let's find E's. So we're going to have red, green, blue. Then we have our 0, 1, 2, 3, 4, 5, and greater than 5. Okay, so we're going to have our row total times our column total. So if I look at 20 here, row total, if I come over, is 41. So we're going to have 41 times column total, so if I come down, is 58. Divided by our grand total, which was 252. For our 10 here, I go over, my row total is 41. Times, and I come straight down, my column total is 67 divided by 252. Now the row total for this first one will be 41 in all of them, so I'll go through and put that in. You can see this is kind of a tedious process by hand. I'm not sure why I even made up such a big example. Okay, so back here to the 5. Again, going over here, row total is always 41. That's why I'm going to put those in. So now I'll put 59 in. Divide by our grand total. For our next one, I come straight down, put 30 in. This one I come straight down, put 19. This one straight down is 10, and this one straight down is 9. Okay, so this one here, row total, if I come straight over here, is 170 times the column total divided by our grand total. So if I come straight down, my column total is 58. Now for all the ones in this row, the row total will always be 170. So I can come across and put 170 for all of them. And grand total is always 252. Okay, so for our next number in that row, come straight down, it's 67. Straight down for this one will be 59. You probably see a pattern. 58, 67, 59, 30, so this will be 30. This will be 19. This will be 10. And this will be 9. This is going to be so easy on the calculator, you'll be wondering why in the world I even showed it by hand. Okay, so for this one right here, our row total is 41. It'll be 41 all the way across. So 41 times our column total. I guess they're both 41s, aren't they? So sitting there looking at that. Sometimes when you're making up numbers, you're not as random as you think. That's what some of this material leads into. Oops. Okay, so for this one here, come straight down, my column total is 58. For this one, come straight down, my column total is 67, and again, you're seeing a pattern. This will be 59, this will be 30, this will be 19, this will be 10, and this will be 9. Okay, well, let's figure this up. Greater than 5. So 41 times 58 divided by 252. And we got 9.43651. I'll take it out to 5 decimal places just because I don't have room for anything beyond that. Okay, this one's 41 times 67 divided by 252. And then we get 10.90079. 41 times 59 divided by 252. 9.676. It'd be a miracle if I don't make a math error somewhere here. So 41 times 30 divided by 252. So I get 4.88095. I'm showing this by hand, not because I want you to do it by hand. I want you to use technology, but because some cases you may have to do it by hand, depending on what class you're in, or if you don't have one of those calculators. It's not a hard process, just very tedious. 3. Now you see some things that are violated already, but again, we'll go with this. It's 127. Because remember what we said in our PowerPoint. All E should be at least 5. Well, obviously these aren't all 5s. Which means the test is not valid. We can't use it. 41 times 10. Divided by 252. Well, we could use it, but making any kind of statement about the validity of it is false. And then greater than 5. We'll have 41 divided by 9, or times 9, divided by 252. $1.46429. Now, a nice part about it is since this was also 41, these values would be the same. So I got 9.43651, 10.90079, 9.676, 4.88095, 3.09127, 1.62698, 1.46429. Now we're going to do the green. So we got 170 times 58 divided by 252. 39.12698. 12698. Next one is 170 times 67 divided by 252. And we get 45.19841. Next one is 170 times 59 divided by 252. By the way, if I don't get the right answer on this, I'm not going to redo it. I think you understand the idea, even though I may be sloppy on adding my numbers and multiplying and so forth. 59. And the next one is 170 times 30 divided by 252. $20.238.1. That 09 rounds. Okay, 170 times 19 divided by 252. 12.81746. Next one is 170 times 10 divided by 252. 6.74 603. And then last one, 170 times 9 divided by 252. Then we got 6.07143. And again, if this was a real life problem, we'd have to look and make sure all E's should be at least 5. If they're not, then we couldn't proceed. Okay, those are E's. Now we want to compute the test statistic. So we got our observed. Now these right here are observed. These are our expected. So we want to do the observed minus the expected squared divided by E. I'm not going to sit there and do all these. I'm going to use Excel. I don't want to sit there and do all that, but I will write the first one so you see the setup on it. Okay, so our next table here is going to be observed minus E squared divided by E. Okay, so let me specifically show red, and I'll show the 0th entry. Okay, so our observed. If I come up to our observed, we observed 20 that were red with 0 children. So observed is 20. Now this is a 0 here, but the O, this is an O, this is observed. Minus the expected. Well, expected is right here. So 9.43651 squared divided by the expected, which is 9.43651. Let's see what that gives us. Okay, so 20 minus 9.43651 close parentheses squared divided by 9.43651. Enter. And this would give us 11.825. 5 decimal places, 0.6. And then we do that same for all these. Then I do red and 1. So I do this one, red and 2, and so forth. It's going to be too hideous to do by hand there, so let me use a little bit of technology. Cheat. Okay, here's going to be my observed. observed. So I got 0, 0, 1, 2, 3, 4, 5, greater than 5. This will be red, blue, what did I say? Green, red, green, blue. Okay, so I'm going to have 20, 10, 5, 3, 2, 1, 0. I'll have 30, 45, 51, 23, 12, 2, 7, 8, 12, 3, 4, 5, 7, and 2. And let me add these together. Don't need to do that for that below, but this is just going to verify I did my data entry right. 41, 170, 41. Okay, let me add these together. $58, $68. Ooh. 10, 45. Oh. I didn't want this to go up to B1. I wanted to go up to B2. Or, yeah, B2. And then fill that over. Okay, 58, 67, 59, 30, 19, 10, 9, 252. Okay, that looks good. Now our expected. This is the number of children going across here. And this will be my red, green, blue. I wonder if I can do this real slick without... Nah, I won't be able to. 9.43651. I could figure it out, but I'd have to put the dollar signs in the right place. I'm just curious. Equals. Okay, the row is not going to change on this. So I'm going to say dollar sign, I want the row total. So dollar sign I, dollar sign 4. That's my row total. Times my column total, which would be columns will change, but the row won't. So I'll do B dollar sign 4, 5. Okay, so the 5 will change, divided by 252. What do you know? This is not as bad in Excel as I thought. Except for I had to really think about it. Okay, this will be equals, see my... if I can fill that up. Okay, so let's see what's going to change here. The I, it shouldn't be I4, it should be I2. That'll be my column total. And then B5. B5 is okay. I think. Now let me fill that across. Okay, now let me think about this one. It's not I4, but it should be I3. And fill that across. Oh, that's pretty straightforward. Okay, those are my expected. And again, obviously, you know, some of them aren't 5, so that's the issue. This is what I want to do, though. So I want O minus E squared divided by E. This is the number of children. And red, green, blue. Okay, equals O, observed. which would be this one, minus the expected, which would be that one, close parentheses squared, divided by the expected, which would be that one, enter. 11.82507. I'm pretty sure that it's right and I'm wrong, but I must have rounded wrong. B4 minus B10. Okay, that looks right. So this right here would be what we're looking for on this. Now this sigma's in front of it. It says we're going to add all these together. So I'm going to do equals sum, beginning parentheses, and I'll click in this first cell, hold down my left mouse button, drag it over, and then do a close parentheses. Assuming I didn't screw up on some of my basic math, our chi-square, our test statistic, is 50.225. Okay. So, chi-square is 50.25. Okay, and let me see. Find the critical value. So, degrees of freedom is equal to row minus 1, column minus 1. Multiply together. Then let's see how many rows. Well, we have 3 rows, red, green, blue. So we'll have 3 minus 1. Number of columns. 1, 2, 3, 4, 5, 6, 7 columns. So we have 7 minus 1. It's going to give us 2 times 6 is going to give us 12. And using alpha. Alpha is 5%. Let's go look that up in the book. 5% for 12. There's 5%. Go down to 12. And it's 21.026. So critical value is 21.026. Okay. If test statistic is greater than or equal to the critical value, our test statistic is greater than our critical value, so it says reject H naught. So for our conclusion, we're going to reject H naught, and we'll accept H1. Again, accept is a pretty strong word. Usually the word you see in books is do not reject. I use reject and accept because students click better with it, it seems like. Okay, so we're going to reject H naught, that they're independent, and say that they are dependent. I made up the numbers. I was trying to make them. Dependent, but so I was trying to falsify the numbers. Now let's do it the easy way, and we'll see if I made a math error somewhere. So p-value approach. Come up with a null and alternate hypothesis. So that's still the same. Input matrix into A. So let's go input that into A. So we're going to put this into A. Now where your matrix is at, your matrix menu, you do second, and this button looks like x negative 1. That's actually your inverse button. We're going to right arrow twice over to edit, do enter on A. And this is asking us for rows by columns. This is 3 rows. So 3 enter, and what did I say, 7 columns? 7 columns. So do 7 enter. And then we'll do 20, enter, 10, enter. 5, 3, 2, 1, 0. 30, enter. 45, enter. 51, enter. 23, enter. 12, enter. 2, enter. 7, enter. 8, enter. 12, enter. 3, enter. 4, enter. 5 inner, 7 inner, 2 inner. Okay, 0, 7, 2, 1, 2, 7, 2, 12, 5, 3, 23, 4, 5, 51, 3, 10, 45, 12, and 20, 38. So exit out. Okay, input matrix in A. Now we want to find a p-value, and we use a chi-square test. So I press my stat, go over to tests, up arrow to chi-square. Now our observed, we just put into A. That's what we just did. B is where it's going to put the expected for us. So let's go ahead down to calculate. I down arrow to it, and I'll press enter on it. Okay, our critical value was 50.25. Let's see if I'm even close. Although I did have Excel cheat a little bit. 50.25. So it looks like I did that part right. But we're doing the p-value approach. Okay. We came up with p is equal to point. Now this is scientific notation. This means move your decimal place 6 places to the left. So I got 1, 2, 3, 4, 5, 1, 2, 6. And it says if p-value is less than alpha, you reject h0. So we would still reject h0, which means we would accept h1, because the p-value is less than our alpha. So you can see much easier to do it with technology. So much better way to do it. Now, remember the condition up above. We said all of our expected frequencies should be at least 5. Well, how would you verify that on the calculator? Well, it puts the expected in B. So if I do a second x negative 1, and I go over to edit, so I right arrow twice over to edit, and down arrow to B, and press enter, you're going to see all the expected frequencies. These right here. 9.4365, 10.901, and so forth. So you can go through here, use your arrow keys, and you could browse through them to see if you see any that are invalid values. Like, it's got to be greater than 5. So these obviously are invalid, which means we can't do the test. But I was just making up bogus data anyway. Realize that making up bogus data, ignoring the fact that they're not at least 5, making up the bogus data, we still came up with that we accept H1. So we accept that they are dependent upon each other. Realize just because you have numbers that seem to tie together does not mean they're really tied together. We know there's no connection between favorite color and number of children you have. But you can put numbers to anything. So there's a lot of different factors that go into research besides just plugging in raw data and saying, well, it must be true because the test says it's true. Okay. Now, homogeneous. In the test so far, consider the values of one of the variables, say the row variable, are assigned by the investigator and are not random. The rows would represent separate populations, and we are interested in testing the hypothesis that the distribution of the column variable is the same for each row. This is known as a test of homogeneous. I have trouble with that word for some reason. That's why I'm using homogeneous. This is kind of what I did here. Not everybody's favorite color is red, green, and blue. I made that up. So this is not random. If this was random, then we use the test we just did. If it's not random, then we'd use this test. But test for homogeneous, exactly the same as test of independence, except H0 says distribution is the same, and H1 says distribution is not the same. We're talking about the distribution over the colors. And I'm not going to do another one on that. I already did one example. But anyway, that's our test for independence and homogeneous.